If you have multicollinearity in your design matrix, like what I showed in the previous exercise, then, well, first of all, if you have multicollinearity in a statistical design matrix, it's likely that there's something wrong and you should investigate and figure out if there is a problem. Of course, in the previous exercise, the problem was that we created a new variable that is a perfect linear combination of existing variables in the design matrix. Nonetheless, it does sort of, this kind of issue does pop up in real world applications. And so, one method that you can use to deal with multicollinearity or a design matrix that is numerically unstable is to use a procedure called regularization. So, we are going to regularize the design matrix. And the way we do this is by shifting the design matrix. So, you can see this intimidating looking equation here, but I would like you to, if you just cover up your screen, ignore this stuff that I'm highlighting here. You can see this is just the inverse of x transpose x. So this is part of the left inverse. And then what we have added on here is three terms here. So this term is the identity matrix. Obviously, you are familiar with the identity matrix. This term here is the Frobenius norm of the design matrix. Now remember, the Frobenius norm is a single number corresponding to a matrix. And gamma here is also a single number. It's generally something pretty small. Okay, so that means that these two terms together produce a scalar, and this is the identity matrix. So that means that we are shifting the design matrix by some small fraction, let's say 0.01, this corresponds to 1%. So we are shifting the design matrix by a fraction, by a percentage of the Frobenius norm. And why are we doing this? Well, this, first of all, guarantees that we are going to have an invertible design matrix here times its transpose. So no matter what the rank of this term here is, this term is going to have a full rank. This is going to be maximum rank, so this will be invertible, even if gamma is very small. As long as it's greater than 0, this will be invertible. It also means that we are only adding a number. We're only modulating the diagonal elements of the design matrix transpose times itself. Okay, anyway, so this is the mechanism of regularization, and I'll talk about this more later and also in the next chapter, but just an important but minor note. Using the Frobenius norm as a regularization term is not very common. It's more common to use other terms like the average of all the eigenvalues. We're going to explore that in the next chapter. I'm just using the Frobenius norm here because I want you to understand the concepts and also incorporate things that you learned from earlier in the book. All right, so start by implementing this term using gamma equals 0 and gamma equals 0.01. And we're going to use the design matrix that we created in the previous exercise. So that was the design matrix with 4 columns, where the last column was a linear combination of rainfall and temperature. So it's a rank 3 design matrix. Okay, so this is the first part, just to print out the sizes and the ranks of these two matrices. And yeah, I'll talk about this when I get to the code. It's funny that, this in theory should be rank 3, but it ends up being rank 2 because it's so numerically unstable. It's just such a terrible matrix. Again, in my humble opinion, NumPy should not even be inverting this matrix. It should give you an error or at least a warning. Okay, so that is like the introduction to this exercise. Now, the meat and potatoes of this exercise, or, the broccoli and potatoes if you're a vegetarian, is to run an experiment. And the goal of this experiment is to explore the impact of regularization on R squared. So you want to compute least squares using the left inverse with regularization varying from 0 to 0.2. And then you compute the predicted data points and then compute the R squared between the predicted data and the observed data. Okay, and then you're going to generate a plot that looks like this using both the original design matrix, which was 3 by 3, For X transpose X, it's 3 by 3, 3 columns in the design matrix. And for the design matrix with multicollinearity, that was the design matrix with 4 columns. Okay. Yeah, and then this is the R squared fit to the data. And I think I will interpret this plot and make a few comments about this plot after I show it in Python. So here is the first part of the exercise where we want to, the main part is here. So we are computing the inverse of the design matrix times its transpose, and this is the desmat m variable, which is the multicollinearity, plus, so inside, we're inverting the sum of these matrices, plus the identity matrix times this variable, gam norm. And you can see that's gamma, which I've set here to be 0.01, times the norm of this matrix. And it's the Frobenius norm, squared Frobenius norm. Okay, so we can run this. I'll actually run this initially for gamma equals 0. And then, yeah, this is hilarious to me that the inverse, it's a rank 3 matrix, but its inverse is rank 2. It's so uninvertible that the inverse actually gets reduced rank compared to the matrix itself. Okay, but then when we set gamma even to be very small, this is 1% regularization, now we have an inverse that is rank 4, and the matrix is also rank 4. All right, so here we are in the experiment. Here we have a little toggle. That's because for chapter 13, the next chapter in this book, there is an exercise that asks you to rerun this code using a different flavor of regularization. So to solve this, basically, I just decided to add this toggle in here, and the reason is that to run this code for this exercise, you also need the design matrix, which means you also need the data. And so, yeah, it just seemed like so much additional code to include in the Python notebook file for chapter 13 that I decided to do it this way. Okay, here's our gamma parameters. We go from 0 to 0.2 in 40 steps. Here I'm just initializing the two R squared vectors. Okay, so here we are looping over the different gammas. And now a lot of this code you've seen before, right? This was just the code that we just ran in the previous cell. So I'm going to create here this lambda term, which gets added to or multiplied by the identity matrix and then added to X transpose X, so the design matrix. And then here I'm using the explicit left inverse method. Now, this code here you can completely ignore. This is for the exercise in chapter 13. If you are familiar with eigendecomposition, you can see that what I'm doing here is setting lambda to be this same parameter gamma by the average of the eigenvalues of the design matrix. Now, if you're not familiar with eigendecomposition, don't worry about that. You're going to learn all about that in the next chapter. Okay, yeah, then the rest of this code is also straightforward. You've seen this all before. We compute the beta coefficients, we get the predicted data value, and we compute the fit to the data. Then all of this code is exactly the same, but it's using the design matrix with multicollinearity. Here I'm just using the regular design matrix with 3 predictors. Okay, and then the plotting. So let's have a look at the figure, and then we can talk about it a bit. So here you see on the x-axis is the amount of regularization, and here on the y-axis is the fit to the data, and yeah, we have for the 2 different models. Now, here's the thing. The more you regularize, the more you are going to decrease the model fit to the data. That's kind of trivial. And the reason why it's trivial is, imagine, let's look up at the left inverse here, what we're actually doing here. Imagine that this number gets really, really big. Let's say instead of being 1% of the norm of the matrix, it's 1,000,000%. So it's a huge number. This is the identity matrix times some really, really large number, and that is going to overpower this number. So the larger this gets, then we shift by a larger and larger amount, then this term here, which we're actually inverting, is starting to look like the identity matrix. It's never going to be exactly the identity matrix because this is always non-zero, but as this gets larger, this term will get closer and closer to the identity matrix, which means that we're, just fitting the data to a sphere, to the identity matrix, which is not terribly interesting. It's not a very useful model just to say that, the data are the identity matrix. There's no relationships between the variables and so on. So the point is that it is kind of trivial that this decreases with regularization. The idea of regularization is not that the model will fit the data better. Instead, it's that the model that you fit to this data set will fit some other data set better. So the generalization performance will increase when you add some regularization. That's the idea of regularization. The fit to your data will be worse, but hopefully the fit to new data will be better. How much regularization to use? It's a very difficult question to answer, and it's an active area of research in machine learning and in statistics. But in general, the idea is you want to add as much regularization as necessary, but as little as possible. So you want to have little regularization, but as much as you need. I want to close this exercise by going back to this basic equation here, because this looks intimidating. There's a lot of lines and curvy things happening in this equation, but this is such a common way of illustrating and implementing regularization that I want to just highlight the importance of this. So you have some matrix times its transpose, and you need to invert that, and then you add or you shift by the identity matrix times something else. And that is such a important and widely used method of regularization. You will see things like this all over the place in applied mathematics, statistics, machine learning, whether it's a simple model or a really sophisticated, complicated model. If you are familiar with the math of this form of regularization, that's really going to help you in advanced applications of machine learning.